Hello again, everyone. Welcome to Chapter 6. So, in this chapter, we're basically doing the exact same thing as last chapter. In Chapter 5, we simply didn't incorporate or include friction in our problems, right? In Chapter 6, we will. So, exact same problem, exact same process, except now we just have another type of force, right? To include in our free body diagram and in our equations. So let's take a look at where friction comes from. Okay, there are two types, which I'll explain in a second, but friction, in essence, right, a very generalized picture of what friction is. Say, for example, we have a box, right, a very lopsided, squished box, on a horizontal floor. So friction, if we were to zoom in to like the microscopic level, both of those objects have a surface, right? The floor has a surface and the bottom side of the box has a surface. Regardless of how many times you buff the floor, right, or smooth it out, the surface has some imperfections. Whether it's wood, whether it's concrete, whether it's even an ice rink, right? As flat as it may feel to your finger, that's still the macroscopic level. On the microscopic level, there are tiny deviations or imperfections. It's not perfectly smooth. The same thing for the surface of a box, right? Or really any object. Regardless of how smooth it feels to your macroscopic touch, your finger, there are some imperfections. And so these two boundaries, right, these surfaces, look something like that. And so the friction comes from these jagged pieces here interacting, right? As one of these surfaces, say, slides or tries to slide that way, that creates, well, a force that way, right? A counteracting force. And so it's this catching that is what you perceive as the friction. So knowing that, we can take, let's get that, okay. So knowing that, let's take a look at, well, if an applied force were to be applied horizontally on this object, right? Let's say it's force F, right? What are the other forces on it? Well, you have the force of the floor going up, preventing the box from falling through the floor, and then the earth pulling down gravitationally on the box with force mg. All right. So actually, I should say before the applied force was there, if the box was just sitting there statically, right, not being touched externally, there's still friction, right? A completely frictionless surface down here is really an idealization. Chapter 5 was lying to you. It was one big idealization, right, with a broad stroke. Chapter 6 is more real life, right? This is what actually happens. So even if you put, say, a hockey puck on the ice rink, it won't move because there is a little bit of friction. So we're going to take a look at that in this chapter. So if there is an applied force now to the right, there has to be an equal and opposite force to the left, preventing that supposed motion to the right, right? And so that's from Newton's third law, right? So this applied force, whatever magnitude it is, there arises a frictional force in the other direction that's equal in magnitude, okay? So this frictional force always tries its best to prevent the box's motion due to the applied force. So now, let's write our force equations. We have x and y here. In order to do this, we need to choose positive directions. So our axes, I'll say that's x and y. I'm not going to draw acceleration for right now. In the x direction, positively, we have that applied force. Negatively is the force of friction. I haven't specified whether it's static or kinetic yet. And that always equals ma. In the y direction, very similarly, we have Fn minus mg equals ma in the y direction. All right, now the difference between static and kinetic comes from the fact of, well, if the box is moving or not. Static, it's not moving. Static friction, right, the static frictional force known as F S, right? F with subscript F for friction and then S for static. This comes into play when there is no motion. It's equal to the coefficient of static friction, which is a Greek letter mu, right? Mu sub S times whatever the normal force is. Now, when you apply a force, like I did there, when you just start to touch the side of the box, just a minuscule force, right? There creates just a minuscule frictional force, right? If you slightly increase that frictional force a little bit stronger, that opposing frictional force increases just a little bit, right? You can keep doing this, pushing harder and harder on that box. Well, the frictional force increases and gets larger and larger, right? Matching that. However, there comes a point where you have some maximum amount that the frictional force, right here, will be able to oppose the applied force, right? Any stronger of an applied force and it will overcome the friction and move the box, okay? So what I should put right here is, let me back it up, is F, I'm going to rewrite it as F static maximum. If I put F with subscript FS max, too many characters. This is the static frictional force, but the maximum static frictional force. And that's equal to mu times Fn. What do you think happens if the applied force becomes greater in magnitude than the maximum static frictional force? Well, if that happens, this box will accelerate to the right because there will be a net force to the right. Right? At that point, the box is in motion. Right? If that applied force is maintained and is greater than the maximum static frictional force, then the box will remain in motion with some acceleration. There's still friction during that motion, though, right? Assuming it stays in contact. So say now, for instance, that this applied force to the right does indeed overcome the frictional force opposing it. Well, then there will be some acceleration in the x direction. Assuming it remains in contact with the ground, the new type of friction now is kinetic friction. So you can write that as F, sometimes you'll see it like that, right? You don't really have a maximum kinetic friction like you do for static because you can never really overcome the amount of kinetic friction, right? It's always there because if the box is in motion, regardless of how fast it goes, there's always contact and thus there's always friction. So you can write it like I have there, or F with a subscript K, okay? And that's equal to the coefficient of friction, mu sub K now, times the normal force. So it's the exact same form as the static, but it's now kinetic, right? This is the friction when the object is in motion. This is the friction when the object is at rest, okay? And because of that, the coefficients are typically like this, right? Mu s is typically always bigger than mu k, right? It's harder to get an object to move than it is to keep an object in motion, all right? So I think that was it for the introductory difference between static and kinetic friction. In the next video, I will go through numerically. I'll plug in some values, and we can see how to solve these types of problems, right? How to determine if an object accelerates or not when there's friction present. Okay, so please watch the next video. Thanks for watching.